So, welcome to our next talk. We are talking now about injecting shellcode for Linux systems into memory. Presented by Renzo. He's the founder of Sector 7 and a security researcher. Give a warm welcome.
Thank you. 1, 2. Okay, thank you. Technical problems. Hold on. Oh. Something's wrong.
Okay, if it doesn't work, I'll go and fetch one.
Right.
It should work.
No. No. Let me check other mode. Maybe this one. No. Yep. Okay, we got an adapter. Perfect. Do you have a cable? Right. The cable first. Okay. Oh, it's on. Okay. Perfect. Now tell me if you see the stuff. Is it visible from the back? Sort of? Okay, let's try it out. Okie dokie. So thank you. I'm sorry for the technical problems. Let's get started. So I'm gonna talk about code injection, shellcode or object code injection in memory only, so without touching disk in Linux. And standard disclaimer, like everything what I say or do is on me, so blame me. Short introduction. I'm Renzo. I come from Poland. I'm a senior security researcher and a red teamer in big multinational company. I'm a former sysadmin and network engineer. Network engineering is my primary background. This is what I do during the threat simulations. Occasionally, I'm a speaker and a trainer, and I also organize a small security conference in Gdynia in Poland. It's called ZIFCon, where we gather red and blue teamers to collaborate, exchange information, and have fun. And as already mentioned, I have a small company, research company called Sector 7, where we research new offensive techniques and refine the existing ones. So today's talk is a result of research done in Sector 7 labs. Short flight plan. I start with what's basically like a base scenario, and then I'll give you some context to that scenario, and then I will dive into the methods I was researching. I have live demos, no recording. I mean, you can of course record, but no movies. Everything is live. For live demos. So yeah, demo gods, I'm coming. And I will wrap up with some OPSEC considerations. So let's start with the scenario. So imagine you are on a pen test or like an engagement, and you have compromised the Linux machine, and you don't have any special privileges, especially root. So we assume that you have some sort of shell. It can be interactive, it can be semi-interactive. It doesn't really matter because most of the methods I'm going to show today is in a form of one-liners. So a chain of commands that you can just throw it into like web shell, and it will work. So with that access, now you want to proceed with your post-exploitation activities, meaning you want to do reconnaissance, privilege escalation, lateral movement, and etc. And at some point you might need additional tools for that. But, and this is one of the objectives, you don't want to upload the tools into the compromised machine's disk. So you want to avoid leaving any artifacts on disk. And to make it run, we will use only what is available on the compromised machine. And as a bonus, some of those techniques can be used to bypass no exec flag set on partitions. In other words, we're gonna play MacGyver, trying to get anything around us to suit our needs. There are two ways of delivering payloads into the compromised machine. One is, so the main communication channel you have, your interactive shell or semi-interactive shell, is your control channel. And then you have two options. One is to send your payload outside of this control channel, which I call out of band. And you just create new, for example, network connection, or I don't know, either anything else which doesn't touch your control channel. The other way is, I call it in-band. So you use your control channel as a data link. In other words, it's like copy-pasting your data through the terminal, okay? And for the purpose of this, demonstrations, I'm gonna be using just SSH session, but it can be anything else, like a netcat or whatever. So for the demos, I've prepared several shellcodes I'm going to be using for the purpose of demonstration. The shellcodes are really simple. They just, you don't have to understand assembly, Intel assembly, but basically these shellcodes are just printing some message on a screen. That's it. So first method, actually it's not a method, but I should mention it, is a tempfs, or temporary file system. So it's a feature of Linux kernel allowing you to store your files in memory only. So the file system just pretends to be like living on disk, but actually it's living in RAM. And if you approach that, this is pretty common nowadays. So tempfs is used. So if you approach that, then you can utilize that. So this is how it looks. There are a bunch of this screenshot is from Debian system, but on many other distributions, this is pretty much the same. So you can use any of those file systems to store your data without exposing it to the disk. But unless there is the system administrator of the system is a little bit paranoid and sets like no exec flag on those file systems that, so it means that you will not be able to run your programs from both file systems. Another method is a GNU debugger, a very powerful tool. Of course, GDB is not common tool installed on the production systems, right? But from time to time, you might find like test or development in workstation. Sometimes I've seen GDB installed on some embedded systems, like routers, for example. And with a GDB, you can do very nice things. Which brings me to the first demo. So what I have here, I have like the left-hand side window is an attacker, and the right-hand side is a victim. I'm just here in a victim. I'm just connected through SSH to the virtual machine running on my laptop. So we have here the shellcode. Now I will assemble it, and this is how it looks. But I need to change that a little bit. Get rid of new lines. Yeah. And now, since we know that GDB is on a compromised machine, then what we can do is do this. So let me walk you through this. So I'm going to run GDB bash under control of the GDB. And then those sets of commands, like -ex, means that I put a GDB command from a command line instead of like you would put in your interactive session in GDB. So what I do here, -q is just quiet mode. So I'm setting a breakpoint on main in bash, then let it run. Then I do something at instruction pointer, on the address pointed by the instruction pointer. Then I continue and quit. So what we need to add is to take this little guy and, you don't see it, yeah. And store it here. But first, I need to tell the GDB how many bytes I'm going to write into the pointer, into the memory pointed by the instruction pointer. So it's here, 66. Yep, it worked. So GDB set the breakpoint here, then started the program. Breakpoint was hit, and then the shellcode was run. Everything in memory. Yeah, so this is basically the same procedure. Now let's be more realistic. GDB is really rarely found on production systems, but what you can find is Python installed by default, and Python has really nice module, really nice module called C-types, which allows you to call C library functions from within the Python. So what we can do is to write a simple loader which will take the shellcode and throw it into the memory and just call it. Okay, so this is how it works. We load. Oh, it's going to die. Whatever. So I'm gonna load libc into the Python memory, then call mmap system call, which creates a new memory region with writable and executable flags. Then I copy shellcode into this buffer, and then do some casting, and I call it. So you probably can see this. Let me show it in here. So here it is. I call the C library. Then I prepare to call mmap. This is not a call to the mmap. It's just preparing Python to the call. Then I do some calculations on how big the buffer should be. Usually the one page would do, but and then I call the mmap. It returns me some pointer. Then I do the copy of shellcode and do some casting, and at the end I call the bastard. So let's assembly the guy. So we need to change it again. Let's change this into this and get rid of new lines. Yeah, you need new line as well. Nope. Right. So I take this shellcode. And go into my Python wrapper or loader. Okay. And now what I'm gonna do is just encode it with base 64 to make it transfer safe. How many of you are doing pen tests? Raise your hand. Okay. So I have a question for you. How should I throw this base 64 blob into the victim? Should I do something like echo my Python and then pipe it to Python? Or should I Python C and then do like base 60, decode here basically? Which method is better from attacker perspective, of course? The first one, this one. And the reason is that if you run it in this form, the whole content of the command line is visible when someone lists the process list. If you do echo something pipe Python, you will see only Python on the process list. That's the key difference. So base 64, sorry, Python. And what I do here is exec something, decode base 64, and we need our code here. Yep, it worked. Let me try if I can show it to you. Yeah. So you can if you can see, this is where the shellcode started to run. So mmap is called, then the shellcode is just writes some data, and here it is. Okay, so let's make things even harder to do, and like, so let's say that we don't have GDB installed, we don't have Python installed, and all tempfs file systems are set to no exec. So what we can do? We can put MacGyver's hat on, right? So there are two things that you can always use, and these are DD tool. DD is just a very simple tool which takes the data from the input, does something with the data, and then throws to the output. procfs is a virtual file system pretending to be like, it's an abstraction layer for your process list. So if you want to access metadata about the processes, you can access this as regular files. So now before I show you the explanation, I'll try to show you the demo, and then we'll see. XXD. Oh, maybe I think we can use the same thing. Yeah. All right. Does anyone knows what will happen? Say again. What memory? Whose memory is it? DD. Yes. So the suggestion is that I'm writing a shell code into the memory of the DD process. While it's copying the data from the input, it puts it into the memory of itself. Okay? And this is correct. But what is this? What the hell is this? Does anyone recognize this? Please. Yes. It disables the ASLR, or address randomization, in Linux. Okay, so the last part is here. What's that? Any bash gurus? All right, I'll leave it for. Let's see if it runs. Oh, it ran. Surprise, surprise. Let me prove that it's. Oh, I'm sending to hell. Sorry. So what is happening at the almost end of this? DD is opening itself, like its own memory, then starts to read. It starts to write the shellcode into its own memory, and then calls the shellcode, which is here. So what we did, I call it Shingenizing a process. So shell injecting the code into the process. So it's really badly seen, but. I took the shellcode from the standard input, then opened opened the memory of the DD process, read the shellcode from the standard input, wrote it into the DD itself on a fly, And then once it's closed, then the shellcode was called. But there are two problems. And one is ASLR, and we have already discovered that there is some feature in a kernel which allows you to disable it. And the second problem is standard input and standard output. The problem is that once the DD finishes copying the data, it closes standard input and standard output. So if your shellcode needs those file descriptors, it will fail, right? So what I'm going to do, so there are two ways to approach this. Either call our shellcode before those close syscalls are called, or do another trick, which I did. And this is what, these are these. So bash provides you a very nice feature which allows you to create a duplicate of a specific file descriptor. So this creates file descriptor number 10, which is a duplicate of file descriptor number 0, so standard input. The same here. Number 11, file descriptor number 11 is a copy of standard output. And then those two file descriptors are passed to the DD, and DD doesn't do anything with them, but the shellcode, before it starts the main job, it calls duplicate system call on file descriptor number 10 and file descriptor number 11, which means that it will recreate the file descriptor number 0 and 1. That's the trick. ASLR, disable ASLR, is this. Linux kernel provides you with a nice feature which is called execution domain or personality, and this feature allows you to run programs which have been compiled on a Unix-like other Unix-like systems, and which expect some specific behavior from the kernel. So, for example, if that program might need like page number 0 being mapped by mmap, then it means that there is a specific personality for this, or the execution domain. And there is, since 2.6.12 version of the kernel, there is a flag which means disable address randomization. And this is what I did. So setarc is the program in Linux which you can change the execution domains. Okay, so now we know how to run the bastard, but yeah, where to write our shellcode. So my first thought was to use PLT, procedure linkage table, which is a simple table. To put it in simple words, it allows you to call external functions from the external libraries. It allows you to resolve the addresses of those functions. The problem with using PLT is that if your shellcode is too large, it might overwrite something in a table which will be called before the shellcode is being called. So it can crash the process. So instead of this, I found fclose library function fclose, which is being called at the very end of DD process. And there are two offsets to this. The fclose is being called only twice. This call or jump. And actually, after some testing, the jump is the main path of the execution. So yeah, we've already seen POC. Oh no, it's really nice, and like cool to see running shellcode, but if you're on an engagement, you rarely use any shellcodes, right? We use elf objects. So how to use these techniques to run a normal program? I've tried to use named pipes, and it fails because mmap call needs mmap needs to seek the file while it needs to read some specific region from the file. The pipe is just like a stream of data, so you cannot seek it, from like byte A to byte Z, right? So it will crash with the error, no such device, as far as I remember. Yeah, here, no such device. Thankfully, to the kernel developers, they have introduced a system called memfd create. And this call, this function, this system call, creates an anonymous file and returns a file descriptor. And the file lives in RAM. Sounds interesting. There's another, this time it's a library call. It's called fexecve, which allows you to perform the same task as execve, but instead of the path to the file, you pass the file descriptor. So from memfd create, we've got file descriptor, and with that function, we can call that by the file descriptor. But the truth is, we don't need this. Instead, we need another shellcode, which is very simple. This part is you've already seen. So this is recreating the file standard input and standard output. Then we call memfd create. So we create an AAA file, capital A, 4 A's, in a memory. And then I ask kindly the process to stop, just to pause. The pause system call is a special system call which allows, makes the process to wait for a signal from the environment. But we will not going to provide any signals to the process. So the exit call at the end here will never be called. And why you will see on the demo. So again, so this is the shellcode. This assembly. We can call the same thing. I'll use the same thing here. The only difference here from the previous demo is that now I want to run it in memory. That's it. That's the only difference from the previous demonstration. So it runs. Hopefully, yes, it's in a process, in a memory. Now, I go to and this is the file descriptor table of the DD process in memory. So we have standard input. So 0 descriptor, 10 is an exact copy, 1 standard output, 11 is a copy, standard error is standard error, and we have something else here. Something which is called memfd AAAA. What is it? What is it? It's a file descriptor? Anyone else? Yes, it is file descriptor. In memory, yes, it's a file descriptor in memory. But what it is that? What is it? What? Yes, it is a link. And what is link? Link is a file. So we have a file in memory already, and it lives in memory only. So now what we need to do is overwrite that file with our tool. I have a VI here, which is just for purpose of for this demonstration. So what I do with this VI is I base 64 encode it. Oh, no. Right, we copy this. And now what we do here, decode and throw it into 3. And paste. So it takes time because this blob of data is really big and I'm just throwing it through the terminal. Okay, we've got it. All right. So yeah, nothing has changed, right? So let's run it. Yay. And to make the final proof, let me show you how it looks like. So here is my interactive shell, right? Then I run DD. Then I call. Let me to make it more visible. Then I call the file descriptor, right? Which is a VI. And then I call shell, which then I call the APS to show you this. Now, so it seems like interesting technique, right? So let's say that you have 10 tools you want to use. Now, do you need to do this the same all over time? Not at all. You can reuse it. For example, let's say just for the purpose of like a proof of concept, let's override this with other tool. And now it's an ID. If you need something else, you can do it all over time, anytime you want. As soon as as far as the process is living in memory, you can reuse that file descriptor as many times you want. So that's a very neat feature. And it's not a bug, it's a feature, right? All right, so this is wrapping up OPSEC, operation security considerations. So, of course, if you are interacting with a machine, you probably will generate some artifacts, even if you try to not touch the disk. So, for example, these can be logs. So I use SSH to connect to the machine, and this produces some log in the SSHD log file, right? If you're using web shell, probably either web server or application server will produce something about your activity. So you have to keep in mind that this still goes on, even if you're trying to not touching disk. The same goes with the process list. It's highly unlikely that someone will spot your strange processes in memory but yeah, it can happen. So if someone lists the processes, you still like it might seem awkward to see like DD and something like super strange command. And the third thing is swappiness, or swapping the memory pages to the disk. There are a couple of things you might try to do to prevent this. So you can in your shellcode you can call mlock all, or mmap to set your memory pages to be not swappable. But to do that, you have to have either IPC lock capability or being root. The same thing you can if you have root, you can turn off the swappiness, so it won't happen. And the final thing is control groups, which you might also give you the possibility to turn off the swappiness, but again you have to be root again. And in case of that, you have enough privileges on C groups at one level, and you turn off the swappiness there. But if in the hierarchy the root C group has the swappiness on, then the memory manager will swap your pages to the disk whenever whatever you have set on swappiness on your C group. So the bottom line is, try to be MacGyver as many times as you can. Reuse any tool you find around you. And the final thing is, and this is the most important thing from this talk, I want you to remember this. You can forget everything what I said so far, but this thing is very, very important. There is only one MacGyver. Only one true MacGyver, okay? That's it. Thank you.
Thank you. Questions?
Yeah, here. Yes. I've prepared the white paper. It will be in format of the blog post. I will post it on my company's sector7.net website soon. It will contain a little bit more than it's in the presentation. Anyone else? If you need, if you want to contact me, I'm running the Zivcon Twitter account. By the way, we have a call for papers open till the end of the year. So if you have any nice research to present, please submit, and we can try to settle it.
There's function in bash process substitution, which creates something like temporary file /dev/fd/something just out of your command. Did you try the attempt to create like the shared library, dynamic library, in like through that base64 encoding and so on? Put it like create through the process substitution bash functionality as the temporary file, and then execute anything that run these functions from this library. I don't know anything about the viability of this route, but just came to my mind.
No. So I don't know. It might work. I was at the beginning. I started to work on this. I was thinking about creating my own loader of objects. So create huge shellcode which will do the same thing as the ordinary Linux loader does. So opens up the file, parses the headers and maps all the regions, etc. But then my friend told me that, hey, there's a memfd create syscall, just use it. And I said, oh, nice feature. But yeah, it might be doable.
And have you ever bumped into system where proc file system was set as no exec?
Process what?
Or is it even possible to set proc file system as no exec?
I'm not saying that. I don't know.
Well,
I said that no exec is set on temporary file system, tempfs. That's a different thing.
Yeah, but did you try if could be mitigation of this attack to set no exec to /proc? Don't.
It's totally unrelated. It doesn't matter. Oh, sorry.
It's better because you rely on running that.
No, I haven't.
/3
I need to try it. Yeah. Good call.
So I didn't really understand what hinders you just to call execve in your when you're at the stage that you overwritten the DD memory.
Mm-hmm.
Now you want to execute something, and then you could simply load your Vim or whatever using execve. I mean, of course, it's not that convenient just piping it to the file and then changing the tools on the go, but would be possible too, I guess, right?
But I'm not using execve at all.
Yeah, but you could, right?
Yes, if you implement the right shellcode.
Okay. Yeah.
So it depends on how it's doable. Yeah, I just created a very simple thing.
Yeah, I just wanted to understand if there's like something hindering that approach. I mean,
No,
I
no,
totally
no.
see that your approach is more useful because you have the file descriptor. Yeah.
To me, it's more useful. I just
Yeah.
need very short shellcode. I don't need to.
Okay. Yeah.
You have to. Yeah, then it would be some sort of.
Because the execve is, I mean, you could just call it from the libc, right? I mean,
Yeah, but
it's already
yes,
in the libc, and you have to point
but
it at
you
the
have
base
to
libc.
point. You have to point one of the arguments of the execve is a path to a file, right?
Okay, I see your point. Yeah.
So it won't give you anything else unless you find a way to point it somewhere else, which is not a file.
Okay.
Right?
Cool. Thank you.
Anyone else? Guess not. Thank you.
Thank you.